This next video lesson is going to cover something called the common ion effect and also buffers. So let's get started. Now first of all, I want to talk a little bit about the word effect, because in science the word effect means something that you can observe, like the Doppler effect or the greenhouse effect. In our case, we're going to observe what happens to an acid at equilibrium, a weak acid specifically, at equilibrium when you add a common ion to the system at equilibrium. Now that common ion is usually the solid form of the conjugate base of that weak acid. So let's start with a weak acid at equilibrium. HF is dissolved into water and you get most of the HF staying together as molecules. And let's draw that a little bit greater proportion. So we've got lots of HF still sticking around, but a very few, or every once in a while, you get some H plus and some F minus dissociating. The Ka of HF is 6.6 times 10 to the negative fourth, which indicates that this weak acid is fairly reactance favored. So the percent ionization is pretty low of hydrofluoric acid. And to give you an idea of the pH of this acid, if you had 1 molar HF and you calculated the pH of that, it would be about 1.59 on the pH scale. Now I'll admit that's pretty low, but to put that in contrast, 1 molar HCl, which is a strong acid, would have a pH of about 0. So we're obviously looking at something that has a low dissociation, percent ionization, and is a weak acid. Now so far, we haven't really discussed anything in dealing with the common ion. We've just been setting up a situation of hydrofluoric acid. And this is everything that's going on right now. Let's just say we have 1 molar in the solution. It's got a pH of 1.59. Now let's add a common ion. Now the common ion you want to choose is something that's going to have the conjugate base of the weak acid. So something with fluorine ions in it. Typically you want to choose something that has a cation that will not affect the pH of a solution. So something that has a low charge or something that has a high mass. So I'm going to choose NaF. Now NaF is going to split up into Na plus ions and F minus. The key is that there will be F minus added to this beaker. So we're going to increase the F minus concentration by adding some NaF. We're also adding some sodium, but I'm not going to include those because they're just going to be spectators. And so what you're going to do is you're going to start to shift equilibrium. This is a Le Chatelier's principal concept. You're going to increase the concentration of F minus in solution. And that's going to force equilibrium to the left. As a result, you're going to increase the concentration of HF and decrease the concentration of H plus in this solution. And so you're going to shift equilibrium to the left. Remember, the Ka is going to try and maintain 6.6 times 10 to the negative fourth. This solution is going to try and keep the same ratio of products over reactants so that this number continues to hold true. And if we boost the F minus, we've got to lower the H plus and boost the products, or excuse me, in this case the reactants, in order to maintain that ratio of 6.6 times 10 to the negative fourth over 1. Now the effect that you will observe is the fact that H plus concentration goes down. And when H plus concentration goes down, that means you become less acidic. And less acidic means the increase in pH. So the results of the common ion effect are that adding the common ion will shift equilibrium to the left. And I realized I had right written there, so I erased it and put left. So again, adding common ion shifts the equilibrium left. As a result, the H concentration goes down and the pH goes up. That is the effect that is observed when adding a common ion to a weak acid at equilibrium. I'm going to show you a problem that you may deal with involving a common ion situation. And it's an equilibrium problem. It's an ice table problem. And this time, instead of having 0 initial product, you have some initial product of sodium acetate. And so it's first important to write out the reaction that I'm dealing with and introduce my initial concentrations. Acetic acid is a weak acid with a Ka value of 1.8 times 10 to the negative fifth. Now initially, I have 0.3 moles in 1 liter of solution, and so it's 0.30 molar. Now initially I have 0 molarity of H+, But because this is a common ion situation, and I know that because I add 0.3 moles of sodium acetate, that's NaCH3COO, and in that case, that introduces the common ion to the solution initially. So I have 0.3 moles of that in 1 liter, or 0.30 molar solution of CH3COO minus. Now the changes occur where I'm going to lose X moles of this, and I'm going to gain X moles of this and gain X moles of that. So my final equilibrium concentrations are 0.3 minus X, X for hydrogen, and 0.30 plus X. Now I taught you in the previous video lesson about how we can take a look at the amount of X lost by the weak acid and the amount of X gained by the conjugate base as numbers that are so small that we consider them to be negligible. And if we do that, what you get is products over reactants, with X being the hydrogen and the other product is 0.30 over the reactant of 0.30, and we'll set that equal to the Ka of 1.8 times 10 to the negative fifth. By doing that, we eliminate the need for the quadratic formula, and what's nice is, in this case, we've got math that is really easy, because 0.3 over 0.3 cancels each other out, and X equals 1.8 times 10 to the negative fifth, and X is your concentration of H+. Now your concentration of H+ can be then calculated to determine the pH of the solution. So I'll do that. I'll take negative log of 1.8 times 10 to the negative fifth, and I will get the pH of 4.74. Now before I wrap up this problem, it's important that I probably check that the percent ionization is less than 5%. So I take the X, which I solve for, and divide it by the original concentration of the acid and determine what the percent ionization is. And as long as it's less than 5%, I can proceed as normal with this problem, and I will not have to go back and do the quadratic formula. Well, I did the math, and the answer here is 0.006% ionization. So I would say that is much less than 5. So I can go ahead and assume that X for the dissociation and the X for the creation of the CH3COO minus is small enough where that can be considered negligible. And as a result, I don't need the quadratic formula. So after all that guessing and checking, not so much guessing, but checking, I can be confident that my answer is 4.74. About buffered solutions. A buffered solution is a solution that contains a weak acid and its conjugate base in the form of a common ion. Typically, when you add an acid and a base together, they neutralize each other, but not when the base that is added to the acid is the conjugate base of that acid. Usually, in order to create a buffered solution, you add a solid that contains the common ion of that weak acid. And our practice problem, in which I just showed you on the last page, was indeed an example of a buffered solution. You had a weak acid at 0.3 molar concentration, and you added 0.3 moles of a common ion, and you created a buffer. Now, what makes buffers unique is that they resist changes in pH when strong acids or strong bases are added to them. So, if you take a buffer and you add an acid, it could be strong or it could be weak, which is why I kind of stepped back on this. I just said acids or bases, not strong acids or strong bases. But if you add the acid or base to the buffer, the pH won't change very drastically compared to if you added the same acid or the same base to pure water. Because buffers are useful in resisting changes in pH, they're very often found in complex biological systems. Your human blood, for example, is an example of a buffer. It has an acid, carbonic acid, and its conjugate base, HCO3-1. And the concentrations of each of those in the blood is high enough in such a way that if the body is introduced to something acidic by ingestion, you don't immediately die, or you're not immediately turned really, really sick. You may become sick eventually. But the blood has a way of absorbing either the acid or base that gets ingested to prevent a drastic change in pH. Picture from the book does a really good job of trying to explain what a buffer really is. I like to think of a buffer as a sponge, and a sponge's job is to soak up something. Eventually the sponge gets full, at which point it's not useful as a sponge anymore, but buffers act the same way. They can either take in acid or take in base, and their pH may change slightly, but won't change as drastically as if the acid or base were added to pure water. Now, I'd like to draw your attention to the middle of this picture, because this is the buffered situation where you have equal concentrations of a weak acid and its conjugate base. Now let's first talk about this right-hand side here. In the right-hand side, you're adding an acid to the buffer. And when you do that, the H plus in the acid added reacts with the F minus in the buffer to create some HF. And as a result, the concentration of HF goes up, and the concentration of F minus goes down. Now this will continue to go up and go up and go up the more acid you add, and this will continue to go down and go down the more base you add. The more acid you add, until eventually you've used up all of your F minus in the buffer. In that case, you've run out of F minus, and we'll talk about this on the next part, but you've broken your buffer. And so that's what I mean by sponge. The buffer will soak up some added acid until eventually all the F minus is used up. At that point, it's nothing more than water. It's no more useful than water, and then the pH will drop significantly with the addition of any additional H+. And so we call that a broken buffer, when you've ran out of the conjugate base because you've added too much acid. Now on the other side of this, you can add a base, just like you could add an acid. So we're going to add a base, and you'll see that some of the base reacts with the HF, and as a result, the concentration of HF goes down. Some of the HF gets converted to, as you can see right here, some of the HF gets converted to F minus because the HF takes the OH and turns it into water. It neutralizes. And then the F minus, as a result, concentration goes up. Now, like the acid, this will go up and up and up and up, and this will go down and down and down and down until eventually you've, again, broken your buffer with a base. When you have no more HF left over in the buffer, and any additional OH will cause the pH of the solution to skyrocket as if it were just added to water. So in summary, a buffer has both the acid and the conjugate base. When an outside acid is added in the form of H+ ions to the conjugate base, it will react with that acid to mitigate the change in pH. And so you'll see a pH go down slightly, but not as much as if it were in pure water. The same is with the base. You add a base to the acid side of the buffer, and that will react to produce water and the F- ion. And the pH may go up a little bit, but it won't go up drastically like it would as if it were added to water.